algorithm will be needed, and we will be discussing that how that modification can be done with the help of a very simple system. Then we will proceed with our next topic. You are probably lagging behind because I could not take a class in the last before Eid, but hopefully we will cover them up in the next subsequent classes. Another announcement is that I was planning to take a class test, but that class test will be deferred because of my engagement. I could not prepare. So you'll have a class test there. Later I will announce. And in your final exam, we will be taking a class test along with your final exam. You will have 4 questions in your final exam. Then after attempting 4 questions, we'll seek your choice to evaluate 3. Then the 4th one will be considered as your class test. The reason is that a written class test cannot be taken blindly. And we don't have that much time, for example, to invigilate you because all teachers are involved in their own purposes. So when we'll have a dedicated slot for exam, we will do that. So equation 26.1 is an equation. You see that a first order differential equation, but it contains something that is very what we call interesting. Can you because you can easily solve this equation. The solution will have this form 26.2. You see that in 26.2 you have a quantity exponential that is changing with time. You have 2 quantities in of exponential form changing with time. Can you see this? One is this and another is this. This time is coming from this quantity. Okay, and you have your input there already present, and that this quantity can be thought as an input. So this input is reflected there as a constant term as output, and this is what the term that contains the characteristic behavior of your time that was present in the input. But this quantity actually, if for example this equation were homogeneous, then what was the case? d1 by dt would be equal to minus 100y, isn't it? Minus 1000y. No source term is there. Then your solution y will be equal to what? Some initial value, because your initial value will be there, say y0, and your solution will be equal to e to the power minus 1000t. You know it from your very basic level. But then you see that in your solution, you will have your 2 time variations there. One is very slow, another is very rapid. You see that time constant of this term is equal to 1 divided by 1000 is equal to how many seconds?
1 millisecond.
1 millisecond, yes. We have another time constant there that is 1 second. Then 1000, for example, difference is there. If this is the case in selecting the time step, it is very crucial of solving this type of problem. This type of problem we call steep type system. Okay, in order to solve them, the algorithm that we learn will not be adequate to solve them. Okay, then why this will not be adequate? Let us discuss with the help of Euler's algorithm. Okay. If we, without considering our source term, if we transfer the equation into a homogeneous form that I have written a bit earlier, then the equation in general form will be equal to d1 by dt equal to minus ay. So if we want to start with our Euler solution, then what will be the thing? You have to start with the initial value. The next value will be equal to what? Your initial value plus the slope multiplied by your step size, isn't it? So your solution will be equal to this. If we have this solution with us, that solution, you have already known the thing. Okay, your derivative dyi by dt is simply equal to minus ayi. If we replace our derivative by minus ayi, this is what algorithm, and if we just rewrite it into a form, something like this. Now tell me, if we have this solution for a non-zero value of y0, is it not your solution decaying, for example, in this way with respect to time with an initial value equal to y0? So this is what our solution that we are expecting. Okay. Now, if you want to solve it numerically, then what will happen? Your numerical solution will not be exactly coinciding with, for example, the solution. It may go in this way, okay, above with some error or even some point can be there in below. But still, it will resemble your the exact solution. Now, the question is that you see that this slope is to be approximated at each step of your numerical calculation. Okay, for example, you are here, you have to estimate the slope. You are here, you have to estimate your slope. You are here, you estimate your slope. Now, when your slope estimation is the thing, the estimation always incurs some error. That means in your numerical calculation of solving differential equation, at each stage of your calculation, you are having some error added with your previous solution. And that is what your error is propagating gradually, and finally it will attain a value. That's why a local error will be there, and similarly a global error will be there. A global error is estimated after finishing your calculation, and your local error should be estimated from at each step of your calculation. So whenever an error is there in each step of your calculation, that error will be propagating to the subsequent steps. That if, for example, this propagation of error is such that your value of your function will be drastically changing. As a result, what will happen? In addition to the accuracy problem, accuracy is what? Accuracy means discrepancy between the actual solution and the solution that you are obtaining. But in addition to the accuracy, we have another problem will occur when your error will be getting amplified. It is in your subsequent calculations. If your error is getting amplified in your subsequent calculation, that what will happen? Then your solution will be inaccurate, of course inaccurate, but still in addition to that, your algorithm will be unstable. For this reason, we have a term, stability is involved there, okay? So how that stability criteria or analysis can be made in our analysis, in our algorithm. So this is what the algorithm we have written. You see, this quantity 1 minus AH for this particular simple example. Although it is simple, but most of the thing can be understood from this simple example. This factor in general, what will happen? What do you expect actually? We expect that this factor must be, the magnitude of the factor must be less than equal to 1, isn't it? Hey, are you there?
Sir, can you explain again, sir?
Can't you understand what I have told you? That this is your y I minus 1 plus next step value. This is your previous step value. It is being multiplied by a factor this. Then if you want to have your solution usable, then what restriction should be there with the factor 1 minus a is?
It should be less than 1.
It should, the magnitude should be, must be less than equal to 1, okay? If it is less than 1 magnitude, okay, that means that this value should be from minus 1 to plus 1. As a result, what will happen? You can easily solve this inequality. Then you can easily see that your A step should be greater than 2 divided by A. If it is 2 divided by A, then this condition will be violated. Then what is happening? Your H must be less than 2 divided by A in order to have a solution where this magnitude will be less than 1, and we will have a solution that will be inaccurate, of course inaccurate to some sense, but your solution will be stable. The reason is that the subsequent values of your error will be less than from your previous error, and your error will not be getting propagated with amplified version. So this is the problem with your step system in particular, that if we have a system, that system where your step size should be determined from the factor, that factor is actually dominating the creating the stiffness of your system. In the previous example, you see that it was dy by dt equal to minus 1000 y. That 1000 is the determining factor of your step size. So from that factor, you can easily choose the step size, and if you can keep your step size below this value, then you will have a solution that will be inaccurate but stable. Now, this algorithm is called implicit type algorithm. Explicit type, the reason is that we are calculating value y next step from the value that was already known to us. Then in order to make this algorithm unconditionally stable, then some modification can be made in the algorithm. Then your algorithm will be what we call taking into a different form. And this type of algorithm is something where the next value that you are calculating will be involved in both sides of your calculation. Okay, you can see this equation and identify what change is or change has been made there. You see that your previous algorithm was yi plus 1 is equal to yi plus dyi by dt multiplied by y. This is what the slope estimated at the initial values or all values. But here you see that this value, slope is estimated at a value that is not yet known to you, isn't it? Is your yi plus yi plus 1 is known to you? So this is not known to you, okay? So in this case, what will happen? Can you solve this equation so easily? Look, this will be very important deciding factor, for example, in your class test as well as your final exam. So be careful about that. Your engagement is enough. Your engagement is a must. So this equation can again be rearranged in this form by collecting the terms in the left-hand side. Then you see that your algorithm is modified in this form. If this is the thing, then you see that your yi magnitude will be tending to 0 if your I is tending to infinity. The reason is that the lower factor, 1 plus a, it is actually will not make, for example, your yi plus 1 greater than yi. That's so for no matter what value of step size you are choosing, the instability will not occur. And this is called unconditionally unstable implicit Euler method. And a solution of your problem is there, try to resolve it. And I have my Excel file where I solve it, but I cannot find it now. So if possible, I will show it a bit later. But actually the thing is that I don't know whether you are considering this effort usable or not. For this reason, actually, I don't know whether there is any change that if I share this thing with you or not. Because until now, no feedback is there. So this is how to implicit algorithm and explicit algorithm both are illustrated. Okay, the example is there, exact solution is presented there. You see that if we choose the value of age that will not fill the criteria, then error will be increasing in this way. And if we choose the step size with fulfilling the criteria, that will give you best stable solution. And again, you see, if we choose our implicit type algorithm, although your result will be inaccurate, but no stability will occur. You can check it by your own. Now, how to apply this algorithm in simultaneous differential equation? You see that if you have a simultaneous equation, I have illustrated one in the earlier days. So we will have our two equations there that we need, they are coupled to each other. Then what you can do, you can apply your Euler algorithm, both implicit type in both of your equation. Then your equation will take this form, 26.8, 26. You can see that in both sides, y. Your first subscript is actually the variable subscript. So next subscript is your time step. Your y1 is the first variable to be determined is at I plus 1 time step would be equal to its whole value plus the slope multiplied by s. Your slope is calculated at the same value yi plus 1. Same is true for your second variable. Then you see that if you want to solve these equations for yi plus 1, even what we have shown for a single equation will not be enough to do that. Then what you need, you have to rearrange this equation into a form. And you will see that that equation will take the form of a simultaneous equation. You see something like this. because we need to find yi plus 1 and yi y1, y1 I plus 1 and y2 I plus 1. Both are unknowns, and both unknowns are involved there in the left right hand side. So if we rearrange this thing, then this will take the form. Okay, our goal is what? We have to find yi plus 1 I
I
plus
plus
1
1.
and 1 I plus 2. Then how to do that? Are not they simultaneous equation?
Yes, sir.
Then you have to solve your side, because this initial value will be known to you. Then you can put into a matrix form. That matrix form will be a coefficient A, and we'll have two values there. One will be y1 I
I
plus
plus 1.
1, y1 I plus 2.
So
Okay,
y2 I plus 1.
I plus 1, exactly. That will be equal to y1 I, y2
Y.
I. Okay, then you can solve it for this value. Now the condition is you have to solve this thing at each of your time step, isn't it? For any for a value of I, you have to, for one time step you calculate it, go to your next time step, then again you calculate it. Okay, only the thing is that your next calculated value will be appearing in the right hand side, isn't it?
Yes, sir.
As your known vector. So this algorithm is stable, but the thing is that it is time consuming. Okay, it is very difficult to calculate manually. In general, for a large problem, you can program it, but each time step you have to solve a set of simultaneous equation. Okay, for this reason it will take time, but it is unavoidable in some cases. The reason is that the conventional algorithm will not work. So with this thing, actually, I am concluding my lecture on ordinary differential equation. You have some other variant of the algorithms. As you know that we are discussing almost all the mathematical technique that we usually use in our engineering. But in practice, for differential equation only, ordinary differential equation, you will find a book of numerical method on ordinary differential equation. So you can easily consider that this is a basic course. We are introducing the fundamental algorithms only. The other algorithms are there, but their basis is also depending on the algorithm we have discussed earlier. You can have a look there. Some examples are there. You can solve them. I have shown something to you earlier. And after finishing my formal lecture, I will also be giving you some flavor of solving electrical engineering problem using those algorithms later after a few days. Okay.
Okay, sir.
So, okay, with this thing, let us start our next topic. Okay, partial differential equation. Actually, the thing is that although we are not considering, for example, our analytical solution, you see, analytical technique is needed. The reason is that unless you have this analytical solution available with you, you cannot, for example, study the effectiveness of your algorithm. For this reason, in differential, ordinary type differential equation, you know the method how to solve them. And I hope you have some introduction of partial differential equation in your differential equation course, and know at least know a few examples how to solve them. So we'll not be discussing that much about analytical one. But if you want to compare something with our numerical one, we have to use this thing, but I will be confining my lecture to such topics that are closely related to electrical engineering, because the general thing is actually a bit difficult for us to associate them with our practical problem that we frequently encounter in our discipline. Okay, the earlier things are a general description. You can have a look there. Already we discussed how to find the finite difference of partial derivative earlier, but I will be discussing the thing a bit detail with a different perspective, just after classifying the partial differential equation. Okay, you see that your partial differential equation actually involve more than one independent variable. In our case, if time is the independent variable, then other independent variable can be the space coordinates. Okay, so in many of our practical purposes, we have our physical quantities that is distributed in the space, and sometimes it is confined in a space. In other cases, it is distributed in the space as well as propagating or going from one place to another. Okay. I don't know to what extent you studied your power system engineering earlier, but some flavor of this type of problem might have been there in your power system course. Okay, in your power system, actually, I don't know. When I ask some question to my student, okay, this is my habit actually, just to explore that what they have gained in their previous lessons. But until now, only few responded. Most of the students actually did not respond. Even when I asked some questions to them in Viva, they could not answer. It appears that they have learned the thing or heard the thing for their first time. So this is very dangerous. Okay. In your power system, do you have any further power system course in your engineering semesters that are left? You have no idea that what courses you are going to do in your next semester. Okay, so in your power system, did you study transmission line?
Yes, sir.
Okay, how many types of transmission line you have? And what is the difference between an electrical circuit and a transmission line? This is a very fundamental question. Okay, if you are seeking a job in your PGC or in other PGCB or in other power sectors, because power sector is what we call a great consumer of our IT engineers. Then how we will answer? Then what is the difference between a transmission line and a power system, electrical circuit? Okay, try to understand it. So this is what the form of a general partial differential equation that involves space only. We have our two variables there. Of course, it is two-dimensional. Okay, then depending on the coefficient associated with the derivatives, A, B, and C, your differential equations are categorized. In a similar way, we categorize, for example, the solution of a quadratic equation. Okay, you can have a look to this table. You see that we have a factor there, b square minus 4ac. And where those constants you have already seen in the equation, 8.7. Then the relative, for example, this factor will determine the type of our category of our partial differential equation. If this factor is less than 0, the equations are called elliptic type. The reason is that the locus will take the shape of an ellipse. And the equation that is written there is an example of elliptic type of equation. Have you seen this equation ever in your courses? This equation? Yes, takle yes ko, no takle no ko. Ekta to koba. You have to say something. That did you see it? Yes or no? Are you there?
Yes, sir.
That means you are perplexed that whether you have seen this thing or not. Okay. Have you seen this equation?
Yes, sir.
Where?
Laplacian operator.
Okay, what is the difference between these two? Mathematically are not the same because in a two-dimensional case, this nebula square is equal to d2 dx2 plus d2 dy2. And another variant of equation is there where source term is there. Del square v equal to minus rho v divided by epsilon. What is the name of this equation? Hey, where you are now?
Poisson's equation, sir. Poisson's equation.
Did you solve Poisson equations in your electromagnetics?
Yes, sir.
All Laplace equation
Yes, sir.
for two-dimensional case?
Yes, sir.
How?
Sir, actually not two-dimensional because our cases were simplified to one-dimensional cases.
Then why you are asking, saying my answer of my question always yes? I asked you, did you solve two-dimensional? You said yes. Because one-dimensional problem is simple integration, okay, ODE. So no, nothing partial flavor can be given. For example, if it is one-dimensional, do we need partial derivative?
No, sir.
If not, can you give me an example of one-dimensional Poisson's equation that can be applied physically in a system? Because if you cannot relate, for example, your mathematics, because we are not mathematician, if we cannot relate our mathematics with our physical system, there is no any meaning of learning mathematics for engineer actually. Actually, no one-dimensional problem physically actually exists for Poisson's equation. Only under certain assumptions we can say that your one-dimensional problem will fit there. For example, if you have a capacitor type problem, for example, that you have infinite numbers of dimension, infinite size of your dimensions of your plates are infinite, and it is aligned with, for example, XY plane with a certain distance, then you can say that if variation of your electric field will be limited, for example, within a certain plane or a certain line, it will not be distributed everywhere. Under this assumption, you can transfer a problem from a three-dimensional to two-dimension, from two-dimension to a single dimension. If we have a single dimensional problem with us, then you can solve it by using simple ordinary differential equation. So if you want to solve them, call them partial, then at least your problem will be two-dimensional type, or at least two variables will be involved. They are independent. Now, if we set this equality equal to 0, we call it parabolic equation. This is the general form of example of a parabolic equation. And if this form is greater than 0, then the locus will be hyperbola. And this type of equation that we are obtaining is hyperabolic equation. I hope all these form of equations are with you in your electromagnetic course. If you want to find a further discussion on it, you can take the recording of class section A. Okay, this is what the example of our elliptic type problem. Okay, in 1A, it is temperature distribution. In 1B, it is somewhat civil engineering problem. And in C, it is our electrical engineering problem. This problem is very important. Okay, in your transmission line, that I asked you that what have you learned in your transmission line? And if you have a transmission line carrying a current and having a voltage in the conductor, then what will happen? You are beneath the line. Okay, did you ask any question to anybody ever that okay, in the roadside you are moving, a transmission line is there moving overhead, and it is a 33 kV. Are this safe for you? If someone will ask, a person will ask you as an electrical engineer, can you answer? That's why electrical engineering learn electromagnetics, okay? So these are the examples. Now I will be going to illustrating the algorithm starting from finite difference method with elliptic equations. And in your elliptic case, here in this book, some examples are there that are actually from other discipline. So we will be illustrating the thing using our problem, okay? So I will be sharing something here. Okay, consider that we have an equation, we need to solve our Laplace equation, okay? Your Laplace equation has this form. In two dimension, the potential is the function of x and y. And then this equation will be equal to If we want to solve this equation analytically, what you can do, analytically you can do that. But if we want to use it, use your numerical algorithm to solve it, then thing is that you have to use your finite difference technique to represent your second derivative of potential in the x direction. And you have to use your finite difference technique in representing your thing in the y direction. Then you add them up, then you will have an algorithm that is your finite difference form of your Laplace equation. That can be, how can we make this thing? Okay, in order to do that, you know that we have to discretize our space. So if you want to discretize our space, then what you can do, we have our x direction. This is your x direction. This is y direction. Then what you need to do, you have to choose a step size in the x direction in order to approximate the derivative del x. Similarly, you have to choose a step size in the y direction just to approximate the derivative in the y direction. As a result, what will happen? You will be in the within your solution region. You will be creating some grid with some point there. So if you want to represent, for example, a one grid, something like this, that this is here you are, and this is one point, this is another point, this is another point, and this is another point. For simplicity, we are considering that our step size in both your x and y directions are h equal. Then this length is equal to h, and that length will also be equal to h. This is equal to h, and that is equal to h. Then if this point is your vxy, then this point will be equal to what? This point equal to
Vx plus hy.
X plus h, and this point will be equal to
Xy plus h. Sorry, y minus h.
And this point will be equal to x, y plus h, and this point will be equal to x minus h into y. So you have used this point around this point xy. Now, if your v potential, for example, vxy is known to you, then you will have a potential at point that is this. You have a potential at point, this is this. You have a potential at that point, this is this. You have a potential at that point, this is this. So if these four potentials are there, and we are assuming that we want to approximate, h is sufficiently small, then what you can do, you can approximate the potential of these neighboring points with the help of vxy by using simple application of Taylor series. For example, if we want to approximate vx minus hy, how can you write it? You just expand it into Taylor series in the x direction. That will be equal to vxy minus h dv dx plus h squared divided by factorial 2 d2v dx2, and we are neglecting the higher order terms. Similarly, if we want to express vhy, and that will be equal to vxy plus h dv dx plus h squared by factorial 2 d2v dx2, something like that. And in the same way, you can do this. Y minus a should be equal to vxy minus h dv dy plus h squared by factorial 2 d2v dy2, and vxy plus a should be equal to vxy plus h dv dx plus h squared by factorial 2 d2v dy, something like this. If we want to, for example, want to mention it, calculate it numerically, instead of using the x and y, we usually use some indices there just to differentiate the location. In this case, what you can do, this location can be called ij. If it is ij, this point equal to what? It is I plus 1 j, and this point will be equal to I j minus 1, and this point will be equal to v I j plus 1, and that point will be equal to v I minus 1 j. So if this point are there, and this is your Vij, and if we add, for example, all this equation together, what will happen? You have your four potential there. That four potentials are V I j minus 1 plus V I j plus 1 plus V I minus 1 j plus V I plus 1 j. That will be equal to what? 4 into Vij, and this term and that term, this term and that term will be cancelled. And all this term will be grouped together just to form equal to what? This is equal to h square by dv by dx2. This is equal to h square dv dy2. So this term will be simply h square into d2v dx2 plus d2v dy2. And
Sir, your sharing has stopped.
is it visible now?
Yes, sir.
So you know that this term equal to 0. So this will be your equation then. If that, what does it mean then? You see that you can write this equation in the different form, that your V I J can also be written in this form, 1 divided by 4 plus all these four potentials considered V1 plus V2 plus V3 plus V4. If we consider, for example, this is V1, this is V2, this is V3, this is V4. That means the potential at the central node would be equal to average of the potential of all the nodes. Okay. So, and this is what for a particular node. You can shift the position of I and j. Again, you will derive these equations. Then what will happen then? If you have a region, then within that region, if you have a region, then what will happen? Within that region, you will have many points. Then how to proceed with the equation? Let me explain it with an example. Okay, if you have a calculator, please get ready with a calculator. If you want to engage in real time. Okay, let us consider a problem. That problem is very simple problem. In your book, a temperature problem is there. Then based on the experience that we will be gathering from this example, you try to solve them. Consider that we have a system, we have a conductor, okay? In this conductor, this side of your conductor is grounded. And you have this conductor is maintained at a potential equal to 100 volt. Then you have this space. In this space, you have been asked to calculate Vxy, how that potential is distributed within that space. This is a very practical problem. Okay, you can consider, for example, this as a transmission system underground, or you can consider this as an overhead transmission line. Say you have a transmission line overhead, which is maintained at 330 kilovolt. You have a ground there. Then between the region, for example, this region, your potential is distributed, and how this potential is getting distributed. If you have been asked to calculate it, you can do that. If your potential is known to you, then you know that the electric field can be calculated from the negative gradient of your potential. You can do that. And you can easily identify what electric field is existing there and at what height you have to place your conductor so that the electric field that is appearing in the man's height will not be detrimental for your health. Do you have any idea about it when you have been introduced to transmission line, that how the height of the transmission line is selected?
Yes, sir. We had a SAC calculation.
You have a SAC calculation, that is good. But if you have a SAC there, but you can consider that this point is the minimum point, and if somebody is there standing, then he will be subjected to some electric field, then how to calculate that electric field, whether that electric field is safe for him. Do you know any standard? For example, using a mobile phone, your mobile phone is also radiating electromagnetic energy. You are using it, you are keeping it in your pocket. And is it safe for you? You have an idea? No idea. So that's why you are learning engineering, okay? If you ask this question to a very general, for example, man, he is not an engineer, probably he could answer. The reason is that they are much conscious about their health problem. For this reason, these things are now appearing in magazines, okay, in newspapers, in many of the things. No, not that many engineering, for example, that engineering knowledge is needed to understand at least the levels, how they are calculated. This is engineering. But what is the safe value? That is not engineering. We have a standard there. Every mobile phone company should satisfy this standard. Otherwise, they will not be allowed to market it. But unfortunately, in our country, okay, you will find mobile phones without any certification. Fake certifications that they are coming from China. The people from this country are going there, ordering them. They are building device in cheap, and they are coming here selling to them. You are buying it, and we don't know how those things are causing health damage to us. For this reason, you see that some of the diseases, okay, are now increasing, but people are not aware of it. Even they are not aware of the devastating coronavirus. Still, many people said they are around it, not wearing masks. Even some people are moving around without violating with the violation of the law. But nobody is caring about it. Today, I have a very shocked news, okay? One of my best friend and teacher passed away this morning. So this is your problem. If you want to calculate it, how to proceed with actually, you can solve it by analytically, by solving Poisson's equation, because this problem is of Poisson's type. And you can solve it numerically. Okay. If you want to solve it numerically, what you can do, first thing is we have to choose H. And in our case, we are assuming that H is equal to del X is equal to del Y. That means we are choosing a square grid. Then how many grid points we need to choose it? Okay. Consider that we will be choosing, for example, say this length is 1 meter. And this is also 1 meter. If we choose a step size equal to 0.25 meter, then how many sections will be there? We'll have in 3 sections, something like this.
Yes,
then
sir.
you can easily connect, for example, this thing. You will see that you will have okay. Then how many nodes you are creating? These are the nodes that are anterior to your system.
9 nodes.
And we have some nodes there that is falling on the boundary. Now the question is that this gap is there that should be maintained. Otherwise, you cannot maintain the potential there. Now you see that you have the nodes that is designated by 0 nodes. They are at the boundaries. And the potentials at the boundaries are specified. Okay, already known. But you have your nodes there, anterior nodes. These anterior nodes, potential you have to find, okay? That means if we consider this potential is V1, this is V2, this is V3, this is V4, this is V5, this is V6, V7, V8, V9. That means these node points are, for example, from V1 to V9, these are unknown. Are not the unknown? You do not know it. Now, how to find them? A very simple thing, anybody can do that. You know the equation there. That if you know the equation there, can you write, for example, starting from node number 1, interior node 1? In this case, you see that your V1 would be equal to what? V1 would be equal to 1 by 4 multiplied by what? Average of 4 potentials of the neighboring nodes. Are not they?
Yes, sir.
So this node potential is grounded 0. This is 0. This node is 0. Another node is there in this boundary 100 volt. Another node is there V4. We do not know the voltage yet. Another node is there V2. We do not know the voltage yet. Is it not the equation for node 1?
Yes, sir.
Similarly, can you calculate the voltage at node 2? Your voltage at node 2 would be equal to what? 1 by 4 into one
V1.
node is there, that is 0. Another node is there V5. Another node is there V1. Another node is there V3.
V3.
In this way, you can go up to your V9. Can you go your V9? V9 would be equal to what? 1 by 4. Your V9 would be equal to
0
VA,
plus 0.
0 plus 0 plus V8
V8
plus
V6.
V6. So how many equations we will have done? If you want to go in this way to complete your, we'll have 9 equations there,
9.
isn't it?
Yes, sir.
And in these 9 equations, how many unknowns we have? Don't
We have
we
9
have
unknowns.
nine unknowns, V1 to V9, yes. Then you can solve them to solve for your unknowns. That's it. So what can you do after writing this equation into this form? You can group them together to put into a matrix form. Say this coefficient matrix and another matrix will be the V unknown matrix node potentials of the interior nodes would be equal to the boundary potentials VB specified there. Boundary values coming from this term, okay? So then what you can invert your matrix A, multiply with B, you will get your V. Or you can solve this equation by using any one of the methods that you learned in your iterative technique to solve it, okay? Here I will try to solve it by using iterative technique by using Gauss-Seidel method, okay? Okay, now if we want to use Gauss-Seidel technique, then how many unknowns we have? We have our 9 unknowns, isn't it? Then
Yes, sir.
initially the voltage will not be known to you. Only the boundary values will be known. Then what you need to do, you have to assume an initial value to proceed with your calculation. So in this type of problem, you can assume a 0 initial value to proceed with your calculation, okay? That means we are calculating, we are assuming a value. That value is equal to say V1 through V9. We are setting equal to 0 volt for 0th iteration. That means these are the initial value. Your superscript indicates the iteration and your subscript is the node potentials, okay? So with this thing, let us start with calculating V1. Your V1 would be equal to what in your first iteration? Would be equal to 1 divided by 4, potential 0 plus 100 volt. No other potential is there in V4 and potential for your V2 is also assumed at 0. That will be equal to what? A calculator, do you have calculator with you? Try to calculate it. Then your next potential point is V2, first iteration, equal to what? 1 divided by 4. And what are the potential involved there? One boundary potential 0 volt. Another is V1, you V1 calculated from your previous
25.
value. 25, your V5 is equal to 0. Your V3 is also equal to 0. Is equal to what?
6.25.
6.25 volt. Your V3 first iteration equal to what? Your V3 involves one boundary, no voltage, another boundary, no voltage, another boundary, has a another point has a voltage 6.25 and the voltage is 0 is equal to what?
1.5625.
Okay. And if you want to calculate your V41 is equal to what? 1 divided by 4. Your one boundary 100 volt. Your V1 is equal to 25 volt. You calculated earlier. And your V7 would be equal to 0. And your V5 is also equal to 0 initially, isn't it? No voltage is there.
Yes,
Is
sir.
equal to what?
31.25.
31.25 volt. Okay, fine. Can you calculate the thing in this way up to your V91?
Yes, sir. Sir, won't the V7, V8, V9 will be symmetrical like the V1, V2, V3?
Maybe or may not be. We will discuss the after calculation. You can easily find that it would be symmetrical. Yes. The reason is that problem is very symmetric. Okay. You will find the value. You can easily check it. Okay. Whether symmetrical or not. It will be symmetrical. Okay. Now the thing is that once this is calculated, is it the final calculation?
No, sir.
No. It is what?
It is the first iteration.
It is the first iteration. Okay. So now the thing is that what you need to do that. In this case, as if your analytic solution is available, then at a particular point, you can easily calculate the, for example, say in our case, your V1 potential is where? V1 is the potential at X equal to 0.25, Y equal to 0.25, isn't it?
Yes, sir.
So if we have a potential analytic solution VA XY available, in that equation, we can put the value V X equal to 0.725 and Y equal to 0.25. Then we can easily find what is the exact value of VA at V1. Then that V1 can be compared with the calculated values of your V iteratively. Then you can set your error stopping criteria there. But if this solution is not available to us, then what you can do for a particular nodal point, consider that this is your Vij. You are at K plus 1 iteration. Then your previous iterative value is known to you. Then you divide this quantity by the present value Vk plus 1. K is the number of iteration. That magnitude, you can set a stopping criteria to stop this calculation. You got my point?
Yes, sir.
Okay. Another, whether you are going to a solution or not, you can easily identify by examining your nature of your solution. Okay. For example, in this problem, you see that plate is maintained at a potential equal to 100 volt. No other potential is there. Then what is your common sense? If we are moving away from this plate, will your potential increase or decrease?
Decrease.
Decrease.
Okay. Is it not the case we are observing in our first iteration?
Yes, sir.
If we just examine the value of V1, 1, V2, 3, and you see that your node potential is gradually decreasing and usually approaching to 0, because when this point V3 is approaching to their 0, it will be exactly equal to 0 because it must satisfy the boundary condition, but we cannot go there. For this reason, the potential distribution we are obtaining will be a coarse distribution, coarse, C-O-A-R-S-E, coarse. Okay, it is not fine. So if you want to make it fine, then one possibility is what? You have to decrease your step size H, isn't it? If we decrease our step size H, then that will, cause our computational time higher. But still, the thing is, will be there depending on the type of the problem. We have no other ways to choosing a small value of H. Another issue is there. Without going to a small function, some other mathematical technique can be applied there to find the potential, because in this case, you will be knowing the potential of V1, you will be knowing the potential of, say, your V4, V5 and V5, but you do not know what is potential distribution here in this region. What you can do then, there exists a mathematical technique by which you can interpolate them. You have already learned the interpolation formula. Okay, so between these 2 points, you can apply your interpolation there to find the potential that will not coincide with any of the other node. Okay. As a result, what will happen then? You can also calculate the equipotential lines there. So if you want to solve it, you can solve it by using your MATLAB programming, or even your MATLAB. We have a PDE tool. PDE tool. Have you heard the name of this tool? Okay. So you see that your solution is actually have this nature. Theoretically, what will happen? Your potential will be distributing in this way, okay? Because this is 0, your potential will be distributing in this way gradually. For example, going to 0, your lines or equipotential lines here will be very spaced and gradually going to 0. Once that potential distribution is known to us, you can easily calculate the electric field by simply taking the gradient of your potential. You know this relationship, don't you know it?
Yes, sir.
Okay. So in your MATLAB, there exists a function, okay, calculating gradient of a vector. It's called quiver. Okay, you can have a look how to calculate the potential function and electric field or vector by using MATLAB. You can explore it. Okay, so in this way, you can proceed with your numerical solution of elliptic type Laplace equation. Now the question is that instead of Laplace, if you have your Poisson, then what will happen? In your Poisson, another term will be added with it, isn't it? That term will contain the charge density. Use charge density, for example, can be there uniformly distributed all over the place. So if you have a charge density rho xy existing here in this medium, and that region is air, then your epsilon 0 will be known to you. Then how to change the algorithm? You see that you have already replaced your algorithm. For example, Vi j plus 1 plus Vi j minus 1 plus Vi minus 1j plus Vi plus 1j minus 4i will be 4Vij will be the replacement of your left hand term, and your right hand term will be equal to rho minus rho ij divided by epsilon 0. You got the point? So if your rho xy is available, then at each point I and j, you can calculate the value of rho, and that will be inserted in this equation. In this way, you can solve your Poisson's equation. So let me go back to your text. The thing that I have already discussed is actually defined in a different perspective here in this equation. Okay, you see that this is the grid, and we have already discussed how to designate the grid into dimension. Okay, here in this case, a temperature problem is identified using their grid notation. Your second derivatives are approximated, and eventually we arrived at the equation 19.8. Is it not the equation we derived in terms of potential?
Yes, sir.
So up to this point, it is not very difficult something to be understood. And actually, when solving this equation, your boundary should have some value, otherwise no meaning of solution. And when a boundary values are fixed, we call them discrete boundary condition, but sometimes we need to know the derivative boundary condition, something like this. Instead of potential, if your electric field is specified in the boundary, then a derivative of potential will be there. Then we need another technique of refining our finite difference equation at the boundaries. So that thing I will discuss later. So with this thing, what you can do, okay, you see that the same problem has been solved here with temperature values at the 4 boundaries are there. So you see that your problem will not be symmetric here, but still the same algorithm can be used there. Okay, that is there. Okay. Now you have your two techniques I discussed. One, you put your equations into simultaneous equation form. Then you apply your matrix inversion there to find the solution, or you can solve iteratively. Okay, so if we put, for example, the equation, this problem also had how many nodes? 9 nodes entered here. As a result, 9 simultaneous equations are there, and these equations are put into this form. Okay. Can you okay, the entries that are blank there actually zeros. Can you, for example, imagine or visualize the shape of your matrix? Is it not a banded matrix that we discussed in earlier chapter when we solved simultaneous equation? Is it not a banded matrix?
Yes,
You
sir.
have a main diagonal, then some minor diagonals are there, and they are separated in such a way, and it is a bit symmetric, something like this, in terms of element, but symmetric in terms of shape, but the value could be different. So what will happen? How many unknowns are there? You see that 9 unknowns are there. Here double subscript are used. As a result, your last value will be equal to T33, isn't it? Here your T33 is equal to T3 is equivalent to T9, the 9th unknown. So this is what the thing, you can invert it, then you will find the thing. Now iterative solution is also discussed there, but the name of the iterative solution here is used for Leibniz method. Actually, whenever a partial differential equation is solved by using Gauss-Seidel method, we call this Leibniz method. Okay, already discussed there. And another issue is also there in iterative based case. The problem that I discussed earlier is actually a naive approach of Gauss-Seidel method. If you want to accelerate, for example, the convergence, that how fast it can converge, what you can do, you can use successive over relaxation technique. So how to do that? You have, without using it immediately calculating value as it is, we have to relax the value by a factor. That factor is called accelerating factor lambda. So if your lambda is specified, you can modify the value before applying it to the next iteration. Okay, we discussed that thing earlier during this thing. This example is solved in this way. You can have a loop there. You see that your T11 is the first interior node potential or temperature, and that is equal to this. Okay, this is coming from what? The initially all interior node potentials are 0. The non-zero value is coming from the potential specified at the boundaries, isn't it?
Yes, sir.
Now in our naive approach, what have we done? We use this value directly to our next calculation, isn't it? But here in this case, if you want to use our relaxation technique, what you need to do? Without using T11 directly to our next equation in finding T121 or 22, this is relaxed in this way. This is the old value multiplied by lambda minus 1. Here lambda is equal to 1.5. Then this is the immediate value calculated multiplied by lambda. Then this is what the relaxed value of T11. And that is used in finding T21. The T21 value is this. Then in finding, for example, T31, you will need T21. But that T21 calculated here is not directly used. Again, it is relaxed. But in the same way, initial value was 0. This is how factor 1 minus lambda. This is what the new calculated value. This is lambda. Then this 2-1 value is used in 3-1, and this process is repeated, okay, until it satisfies the stopping criteria, okay. So with this thing, I want to conclude my today's lecture. In the next day, we'll be starting with the next type of, we'll discuss something about derivative boundary condition. Then we'll be going to our next solution of next type of differential. Stop recording.